Somewhere past Neptune, 6 billion miles from where you're lying right now, something is happening that should not be possible. A spacecraft just woke from a 321-day sleep, and the first thing its instruments found was dust. Not a trace of it. Dust in quantities 2 to 3 times higher than any model predicted, drifting through a region scientists had confidently declared empty decades ago. That's just the first crack. Tonight we're going beyond the last planet on every solar system diagram you've ever seen, into the Kuiper Belt and the frozen frontier that lies past it. We're going to walk through worlds that are too small, too cold, and too far from the sun to be doing anything at all, and yet they are flowing, cracking, venting gas, maybe even erupting. We're going to look at a boundary that was drawn cleanly in every textbook for 30 years, a sharp edge near 50 times Earth's distance from the sun, and watch that edge quietly dissolve under new evidence. And we're going to sit with the strangest part of all, a handful of distant orbits out past everything we've mapped that seem to be pointing at something massive, something unseen, something no telescope has confirmed yet. By the end of tonight, you'll understand exactly why the space beyond Neptune is stranger, colder, and far less finished than anyone ever told you. Get comfortable, hit subscribe if you're new here, and let's go looking into the dark. Now let's slowly ease into this. Part 1. The map that lied to you. Every diagram of the solar system you have ever seen tells a small, comfortable lie. 4 rocky worlds close to the sun, a belt of asteroids, 4 gas giants strung out in stately order, and then Neptune, blue and distant, sitting at the outer edge of the picture like a period at the end of a sentence. Beyond it, the diagram usually just fades to black. Maybe there's a dotted circle hinting at Pluto's old orbit, maybe a small label reading Kuiper Belt tucked into a corner like an afterthought. The visual message is unmistakable. This is where the interesting part of the solar system ends. Neptune is the wall. Everything past it is scattered debris, too small, too dark, and too far away to matter. That impression is not a little bit wrong. It is wrong in its foundations. Beyond Neptune lies a vast, populated, gravitationally sculpted region stretching for billions of miles into the dark, containing tens of thousands of known worlds, and by every serious estimate, hundreds of thousands more that no telescope on Earth has ever detected. It holds dwarf planets with mountains and glaciers and what might be active volcanoes. It holds fossils from the birth of the solar system, preserved in ice for 4.5 billion years, essentially untouched. And it holds a debris environment that, according to instruments now drifting through it in real time, is far larger and far stranger than any model of our solar system predicted. To understand why this region unsettles the people who study it, you first need to feel how far away it actually begins. Neptune orbits the Sun at an average distance of about 4.5 billion kilometers. Sunlight, the fastest thing that exists, takes roughly 8 minutes to reach Earth. To reach Neptune, that same beam of light needs slightly over 4 hours. Send a radio signal from Earth to a spacecraft near Neptune, and you would wait more than 8 hours just for it to arrive, and then another 8 for any reply. At that distance, the Sun is still the brightest thing in the sky by a wide margin, but its warmth has almost entirely drained away. The sunlight reaching Neptune is roughly 900 times weaker than what falls on your skin on an ordinary afternoon on Earth. Noon on Neptune looks something like deep twilight here, bright enough to see by, but with none of the heat. And Neptune, for all of that distance and all of that cold, is only the beginning of what lies beyond. For most of the 20th century, physicists had good theoretical reasons to suspect that Neptune could not simply be the last thing out there. The solar system formed from an enormous rotating disk of gas and dust, and there was no obvious reason for that disk to have stopped producing material right at Neptune's orbit and nowhere else. In 1943, the Irish astronomer Kenneth Edgeworth proposed that a reservoir of small icy bodies should exist past Neptune, leftovers from the original planet-building process that never quite finished. In 1951, the Dutch-American astronomer Gerard Kuiper made a similar case, arguing that the outer solar system should contain a thin belt of frozen debris. Too sparse to ever coalesce into a full planet, but too massive to have simply vanished. History, somewhat unfairly, gave Kuiper's name to the region, even though Edgeworth arguably got there first. But predicting something and finding it are two very different kinds of work. For decades, the only known object beyond Neptune was Pluto, spotted in 1930 by a young amateur astronomer named Clyde Tombaugh, working through stacks of photographic plates by hand. Pluto held the title of ninth planet for 76 years, and for most of that time it seemed almost tragically alone, a single small icy world orbiting at the edge of everything anyone knew. Astronomers searched for companions. They found nothing. The Kuiper Belt stayed exactly what it had always been, a good idea without a shred of direct evidence behind it. The problem was technological, not theoretical. Objects beyond Neptune are small, typically ranging from a few kilometers to a few hundred kilometers across. They are dark, reflecting only a sliver of the already feeble sunlight that reaches them, and they move at a crawl against the background stars, because an object out there can take a century or more just to complete a single loop around the sun. Finding something that's faint and that's slow requires enormous telescopes, extremely sensitive digital cameras, and the patience to compare images taken hours or days apart, searching for the one point of light that has quietly shifted position while everything else stayed still. None of that existed at the necessary precision until the very end of the 20th century. The breakthrough finally came in 1992. Two astronomers, David Jewett and Jane Liu, working at an observatory in Hawaii, spotted a faint object they designated 1992 QB1. It was small, roughly 160 kilometers across, orbiting the Sun well past Neptune at a distance of about 4 times the Earth's sun gap. It was not Pluto, it was not a comet in any familiar sense. It was exactly the kind of cold, ancient, icy body that Edgeworth and Kuiper had imagined more than 40 years earlier, sitting quietly in the dark, waiting to be noticed. That single discovery cracked the outer solar system wide open. Within a few years, dozens more objects turned up, then hundreds, then thousands. Telescopes around the world swung toward the same faint stretch of sky past Neptune's orbit and kept finding more. Each one a frozen leftover from the earliest days of the solar system, drifting in the dim outer dark. The theoretical Kuiper Belt became an observational fact, and it turned out to be far richer and far more structured than a simple ring of scattered gravel. As of the mid-2020s, more than 5,000 of these trans-Neptunian objects have been catalogued, and that is almost certainly just the visible fraction of something enormous. Models suggest the Kuiper Belt contains something on the order of 100,000 objects larger than 100 kilometers across, and potentially billions of smaller fragments down to the size of boulders. The total mass of the belt is modest, a tiny fraction of Earth's, but it is spread across a volume of space so large that human intuition struggles to hold it. This is not a thin ring drawn cleanly around the sun. It is a broad, thick, donut-shaped region stretching from somewhere near Neptune's orbit outward to 50 times the Earth-Sun distance, and, as we are about to see, quite possibly much, much farther than that. And that shape is not an accident. Neptune did not simply happen to sit at the inner edge of a debris field that arranged itself politely. Neptune built this place. Its gravity is the single dominant force that carved the Kuiper Belt into the shape we observe today, protecting some populations while quietly destroying others, over billions of years of patient, relentless influence. Understanding exactly how that happened, how one planet's gravity could sculpt a frontier this large, is where we're going next. Part 2. The gravity that builds and breaks. When the solar system was young, Neptune was not orbiting where it sits today. The leading model of early solar system evolution, developed by a team of researchers and named after the French city where it took shape, suggests that Neptune formed much closer to the Sun and then slowly, patiently migrated outward over hundreds of millions of years. As it drifted through the primordial disk of icy debris left over from planet formation, its gravity reached out and touched nearly everything in its path. Some small bodies were flung inward toward the Sun, becoming the ancestors of the short-period comets that occasionally streak through our night sky. Some were hurled outward onto wild, stretched-out orbits that would carry them hundreds of times farther from the Sun than Earth ever travels, before swinging back on journeys lasting centuries. And some, in a stroke of gravitational luck, were captured into something called resonance, a stable rhythmic relationship where a small object's orbital period locks into a precise ratio with Neptune's own. These resonances are not some abstract mathematical curiosity confined to a chalkboard. They are physical safe harbours, and they are the reason the Kuiper Belt has the shape it has today. The most famous of them is a 2 to 3 resonance, where a small object completes exactly 2 trips around the Sun for every 3 that Neptune makes. Pluto sits inside this resonance. So do thousands of other icy bodies, collectively known by a name that echoes Pluto's own. Their orbits are not identical to Pluto's, but they share that same protective rhythm with Neptune, a rhythm that keeps them safe even though their paths physically cross Neptune's orbit twice on every loop. Without that resonance, Pluto would almost certainly have been ejected from the solar system entirely, or smashed apart in a collision with Neptune billions of years ago. Instead, the resonance functions like a shield, a gravitational alibi that keeps Pluto and its neighbours tucked into a pocket of stability that Neptune itself created during its long migration outward. Other resonances exist at other ratios, each one capturing its own small population and locking it into place. Together, these resonant families form the skeleton of the Kuiper Belt structure, an invisible scaffolding of orbital mechanics, holding thousands of icy worlds in careful, choreographed patterns. Between these resonant pockets lies what astronomers call the classical belt, sometimes given the nickname the cold classical population, because its members travel on calm, nearly circular orbits with very little tilt relative to the plane where the planets orbit. These are objects that appear to have formed roughly where they sit today, largely undisturbed by Neptune's long migration. Their orbits are gentle. Their surfaces tend to carry a distinctive deep red hue, a colour signature linked to ancient organic compounds that have spent billions of years being slowly cooked by cosmic radiation. This cold classical population is widely considered the most pristine, most primordial sample of material anywhere in the solar system, a population that has been sitting quietly in cold storage since before Earth had finished forming. In contrast, there is a far more chaotic population known as the scattered disk, made up of objects on wildly elongated, steeply tilted orbits that can carry them from close to Neptune out to hundreds, even thousands, of times Earth's distance from the Sun before looping back. These were not gently placed on their paths. They were thrown there, flung outward like stones from a slingshot during close gravitational encounters with Neptune. Their orbits remain unstable over long stretches of time, and many of them are destined to be perturbed again someday, either ejected from the solar system for good or nudged inward to eventually become the short-period comets we occasionally glimpse from Earth. The single most massive known dwarf planet, discovered in 2005, belongs to this scattered population. Its discovery, along with the recognition that it was comparable in size and mass to Pluto, forced the astronomical community to confront a question it had been quietly avoiding for years. If Pluto counted as a planet, then this newly found world had to count as one too, and so did every other body of similar size waiting to be discovered out there in the dark. The International Astronomical Union resolved the dilemma in 2006 by creating an entirely new category, the dwarf planet, and moving Pluto into it. People still argue about that decision at dinner tables and on comment sections to this day, but the underlying scientific reality was never really in question. Pluto was never alone out there. It was simply the first member of a much larger family that we happened to notice first. That family has only grown since. There is a world with nitrogen glaciers and a thin, fragile atmosphere. There is an egg-shaped body spinning so fast that its own rotation has stretched it into an elongated shape, trailing a family of collisional fragments and even a faint ring system, discovered almost by accident when it passed in front of a distant star. There is a methane-rich world, roughly 2/3 Pluto's size, taking more than 3 centuries to complete a single orbit. There is a reddish world further out in the scattered disk, accompanied by its own small moon. And these are only the objects large enough and lucky enough to have already been formally classified. Dozens more candidates sit in the queue, almost certainly qualifying, waiting for enough follow-up observation to confirm it. In the space of a single human generation, the outer solar system went from holding exactly one confirmed world beyond Neptune to holding thousands. And that explosion of discovery revealed something else, something the early theorists never quite anticipated. The Kuiper Belt is not a uniform slab of leftover gravel evenly spread through space. It has architecture. It has population boundaries, density variations, empty gaps standing right beside crowded clusters. Some of this structure is beautifully explained by Neptune's gravity, the resonant families, the calm, cold classical population. The way the belt's inner edge lines up almost exactly with Neptune's own orbit. All of it follows naturally from well-tested physics and decades of careful modelling. But other features of the belt have refused to fit so neatly. The outer edge of the classical Kuiper Belt appears, in every survey conducted so far, to drop off sharply somewhere near 50 times Earth's distance from the Sun. The density of known objects declines steeply right around that mark, and beyond it, the population of confirmed worlds thins out dramatically. For years this was treated as settled fact, the genuine outer boundary of the belt, the precise point where the original disk of material simply ran out, or where some ancient dynamical process had swept the region clean. It was a clean, satisfying explanation. It fit neatly into a diagram, and it has become increasingly difficult to defend. Because the trouble, as it so often does in this field, started with the dust. A spacecraft currently drifting through this very region carries an instrument built for exactly one purpose: to count the impacts of microscopic dust particles along its flight path. Particles produced by ancient collisions between Kuiper Belt objects and by the steady, grinding bombardment of interstellar dust streaming in from beyond the solar system entirely. Every model built before this spacecraft arrived out there predicted that the density of that dust should peak somewhere near the heart of the classical belt and then fall away quickly, following the belt's supposed edge down into near emptiness. That is not what the instrument found. And the story of what it found instead, and what it might mean for everything we thought we understood about where our solar system actually ends, is where we're headed next. Part 3. The dust that should not be there. Picture a spacecraft the size of a small piano, drifting through a region of space so dim that even at local noon, the sun looks like nothing more than an unusually bright star. It carries a small, unassuming instrument bolted to its frame, built years earlier by a team of students and named after the woman who inspired the project. Its job is simple in concept and brutal in execution. Count the impacts of dust particles too small to see, grains of ice and rock left behind by ancient collisions, striking the spacecraft's detector panel as it plows onward through the dark at roughly 14 kilometers every second. For the first several years of the mission, this instrument behaved exactly as expected. As the spacecraft approached the heart of the classical Kuiper Belt, somewhere around 40 to 42 times Earth's distance from the Sun, the dust density climbed, just as the models predicted it would. This was the region where the population of icy bodies was thickest, where ancient collisions between Kuiper Belt objects were most frequent, grinding surface material into fine powder and scattering it into space. Every model built before the spacecraft's launch agreed on what should happen next. As the craft continued outward, past the belt's supposed edge near 50 times Earth's distance, the density of parent bodies should thin dramatically, and the dust should thin right along with it. It did not. As the spacecraft crossed 45, then 50, then 55 times Earth's distance from the Sun, the dust counter kept recording impacts at rates 2 to 3 times higher than any existing model predicted it should. There was no decline, there was no falling edge. The dust simply kept coming, steady and elevated, as though the spacecraft had never actually left the crowded heart of the belt at all. A study published in an astrophysics journal in early 2024 laid out these unexpected readings plainly, an elevated dust flux persisting all the way out past 5 times Earth's distance, with no sign whatsoever of the drop-off that decades of modelling had promised. A follow-up analysis the following year dug even deeper into the numbers, trying to figure out whether something about the physics of the dust grains themselves, rather than the population producing them, might explain the discrepancy. There were real candidates worth considering. Perhaps the icy grains drifting through this region were being slowly stripped of their volatile coatings by ultraviolet light, a process that would shrink them and make them more responsive to the gentle outward push of sunlight itself, known as radiation pressure. A smaller, lighter grain rides that pressure further before anything stops it, meaning dust produced closer to the Sun could simply be drifting farther outward than anyone had assumed, stretching the dust cloud well past its true source population. This is a real physical effect, and it likely explains some fraction of what the spacecraft detected. A companion study modelling the different behaviours of icy versus rocky dust grains found that volatile rich particles do indeed travel further under the influence of these forces than purely rocky ones, adding weight to this explanation. But even accounting for these effects as generously as the physics allows, a significant gap remained. The dust levels the spacecraft was recording could not be fully explained by grains produced back in the crowded heart of the belt simply drifting further than expected. There was a third possibility on the table, and it was the one nobody particularly wanted to be true, because of what it implied. What if the population of parent bodies producing this dust was not confined to the classical belt at all? What if there are Kuiper Belt objects, small ones, faint ones, sitting well below the detection threshold of every telescope survey conducted so far, quietly orbiting at 60, 70, even 80 times Earth's distance from the Sun? Their mutual collisions and their steady bombardment by interstellar dust streaming in from beyond the solar system would produce exactly the kind of elevated local dust environment the spacecraft was flying through. This explanation requires no exotic new physics. It requires something simpler and, in its own way, more unsettling. It requires more material out there than anyone accounted for. More objects, more collisions, more of a solar system than the maps currently show. These three explanations are not mutually exclusive, and researchers studying the data generally agree that all three effects are probably contributing something to what the spacecraft is recording. But the third possibility, even if it only accounts for part of the excess, quietly rewrites the outer boundary of the solar system. It suggests that the sharp edge near 50 times Earth's distance, the one drawn so confidently in decades of textbooks, may not be a true edge at all. It may simply be the limit of what our best telescopes, straining against the faintness and slowness of these distant worlds, have managed to see so far. Supporting evidence soon arrived from an entirely independent direction, and it did not come from a dust counter at all. It came from deep imaging. The mission team behind the spacecraft partnered with a large ground-based telescope in Hawaii, using its wide-field camera to conduct a careful, painstaking search directly along the spacecraft's own flight path, hunting for faint, slow-moving points of light that no previous survey had ever noticed. In 2024, the results of that search were published, reporting the detection of several candidate trans-Neptunian objects sitting at distances stretching out toward 90 times Earth's distance from the Sun, nearly double the accepted edge of the classical belt. The word candidate carries real weight here, and it deserves to be treated carefully rather than breathlessly. The orbits of these newly spotted objects are not yet fully determined. Confirming an orbit for something this faint and this slow requires tracking it across multiple years, watching how its position shifts against the background stars over seasons and even decades, before its true path around the Sun can be pinned down with confidence. These candidates could belong to the wild, elongated, scattered disk population. They could be unusual outliers of the classical belt on strange orbits. Or they could be the first faint signals of a population that has simply never been surveyed before, sitting quietly in a gap between what we know and what we've only begun to suspect. The principal investigator behind the spacecraft's mission described these combined findings, the elevated dust and the candidate distant objects together, as evidence for what he called a possible second Kuiper Belt, an extended outer population sitting beyond the classical belt's accepted boundary. That is a striking phrase, and it has understandably generated both excitement and caution across the field in roughly equal measure. It is not a confirmed discovery. It is an interpretation of limited, though genuinely puzzling, data, but the timing of this uncertainty matters more than it might first appear. For decades, that sharp outer edge near 50 times Earth's distance was not simply an observation. It became a foundational assumption, a boundary condition baked directly into models of how Neptune migrated during the solar system's youth, into calculations of how much material the original planet-forming disk actually contained, into an entire generation of theoretical work built on the confident premise that we knew, at least roughly, where the debris field stopped. That assumption is now under active revision, and the consequences of getting it wrong ripple outward through every model constructed on top of it. Because the Kuiper Belt is not simply a scattering of icy leftovers drifting aimlessly through the dark. It is a fossil record. The sizes of these objects, their orbits, their compositions, their spatial distribution across the belt. All of it encodes information about the exact conditions that existed when the solar system itself was still forming, more than 4.5 billion years ago. The structure of the belt tells us where the giant planets once sat, how violently they moved through the material around them, and how much raw material was actually available in that primordial disk to begin with. If the belt genuinely extends further than anyone assumed, if meaningful populations of objects exist beyond 80 times Earth's distance in a region long assumed to be nearly empty, then the original solar nebula was almost certainly larger and richer than current formation models assume. It means Neptune's gravitational reach shaped a far larger volume of space than anyone calculated. And it means the transition from our tidy, well-ordered planetary system into the true chaotic frontier beyond it is not a clean line at all, but a long, gradual, poorly mapped fade into darkness. To feel the scale of what we are actually talking about, imagine compressing the entire solar system down into a model small enough to fit in your mind. If Earth orbited just 1 meter from the Sun in this model, Neptune would sit 30 meters out, and the accepted outer edge of the classical Kuiper Belt would land at about 50 meters, roughly the size of a generous backyard. That already sounds enormous, but the scattered disk reaches far beyond even that boundary, one of the most distant confirmed objects in the solar system. Discovered in the early 2000s, follows an orbit that carries it from about 76 times Earth's distance at its closest approach to the Sun, out to more than 900 times that distance at its farthest point, a single lap around the Sun taking well over 11,000 years. On our 1 meter model, that object's most distant point would sit nearly a kilometre away from our Sun. And beyond even that lies something we have never directly observed at all. A theorized spherical shell of icy material believed to be the true source of the long-period comets that occasionally streak toward the inner solar system from every possible direction, arriving on orbits that can only be explained by a reservoir extending tens of thousands of times Earth's distance from the Sun. On our model, that outer shell would stretch 50 to 100 kilometers away in every direction. The Kuiper Belt, in other words, is not the outer edge of our solar system. It is only the beginning of it, and Neptune's role in shaping everything within it turns out to be strangely contradictory, simultaneously the region's guardian and its slow, patient destroyer. A paradox that becomes clear the moment you look closely at what Neptune's gravity has actually been doing out there for the last 4 billion years, which is exactly where we're headed next. Part 4. The gravity that gives and the gravity that takes. There is something almost paradoxical about Neptune's relationship with the vast frozen population that surrounds it. On one hand, Neptune is a protector. Its resonances, those precise rhythmic partnerships we touched on earlier, act as safe harbours, locking entire families of objects into orbits that can survive for the full lifetime of the solar system without ever suffering a catastrophic close encounter. Pluto has been circling the Sun in lockstep with Neptune's gravity for over 4 billion years. crossing Neptune's orbital path twice on every single lap, and never once colliding with it, never once being flung away, because the resonance keeps the timing exact. When Pluto is closest to the Sun, deep inside Neptune's orbital path, Neptune itself is always safely on the other side of its own orbit. It is a gravitational choreography so precise it borders on elegant, and it has protected thousands of similar objects for the vast majority of the solar system's history. But that same gravity, just slightly recalibrated, becomes something closer to a slow, patient eraser. Any object that drifts too close to Neptune without the protection of a stable resonance is at the mercy of a very different outcome. A single close pass can send it careening inward toward the warmth of the inner solar system, transforming it into a short-period comet doomed to slowly boil away over a few thousand orbits. Or it can be hurled outward, joining the wild, elongated population of the scattered disk, thrown onto an orbit that might carry it hundreds of times farther from the Sun than Earth ever travels. Or, in the most dramatic outcome of all, it can be ejected from the solar system entirely, flung out into the emptiness between the stars, never to return. Over the 4.5 billion year history of the solar system, this process has never stopped. Neptune has been steadily, relentlessly sorting the material around it, protecting a favoured few while scattering the rest. The Kuiper Belt we observe today, with all its careful structure and internal families, is not the original population that formed alongside the young Sun. It is a remnant, a survivor, a fraction of what was originally there, filtered and thinned by billions of years of gravitational sorting performed by the planet next door. And this erosion has never paused. It is happening right now as you listen to this, just as it was happening when the first complex animals crawled onto land on Earth, just as it was happening before Earth had a moon. Objects near Neptune's orbit continue to be perturbed today. Some slip inward to eventually become the short, bright comets astronomers still occasionally spot-streaking through the inner solar system. Others are flung outward, feeding the scattered disk with fresh material even now. The Kuiper Belt is not a fossil frozen in time since the solar system's youth. It is a slowly draining reservoir, patiently thinned by the gravity of its enormous blue neighbour, one quiet gravitational nudge at a time. At the same time, Neptune's reach has limits. Beyond roughly 50 times Earth's distance from the Sun, its gravitational influence weakens to the point where its ability to meaningfully perturb objects becomes almost negligible. This is, in fact, one of the deepest reasons the sharp edge of the classical belt was so puzzling to begin with. If Neptune's gravity genuinely cannot reach that far with any real strength, then something else must be responsible for the apparent cutoff, and nobody has a fully settled answer. Perhaps it reflects the true natural outer limit of the original disk of gas and dust the solar system formed from. Perhaps a passing star, drifting close to the young Sun in its birth cluster billions of years ago, gravitationally stripped material from the outer edges of that disk before it ever had the chance to coalesce. Or perhaps, and this is the possibility that keeps a certain corner of planetary science awake at night, there is a massive, undiscovered body out there whose gravity has been quietly shepherding the boundary from a distance we haven't yet resolved. None of these explanations has been confirmed. Each one, if true, would ripple outward through the rest of planetary science in different and significant ways. What is confirmed, without any real dispute, is that the known Kuiper Belt, even setting aside every question about extensions and second belts and hidden planets, is already a staggeringly complex place. It hosts multiple dynamically distinct populations, shaped over billions of years by gravitational interaction with Neptune. It contains at least half a dozen recognized dwarf planets, and probably several dozen more candidates still waiting for formal classification. Its members range from tiny fragments only a few kilometers across up to icy worlds well over 2,000 kilometers in diameter. Their surfaces span an enormous range of colors, from neutral grays to the deepest, darkest reds in the solar system, evidence of wildly different compositions and billions of years of different radiation histories. Some are rich in water ice. Some wear coats of frozen methane and nitrogen. Some carry the dark, reddish residue of organic compounds that have been slowly cooked by cosmic rays for longer than complex life has existed on Earth. They are not simple. They are not uniform. And they are absolutely not, whatever the old diagrams implied, just frozen rocks drifting through nothingness. To understand exactly how far this complexity goes, it helps to start with the world that started it all. Before any spacecraft had ever reached the outer solar system, before the Kuiper Belt had even been confirmed to exist, there was Pluto. Discovered in 1930 by a young, self-taught astronomer working through box after box of photographic plates by hand, comparing images of the same patch of sky taken days apart, hunting for the one point of light that moved when nothing else did. For 85 years afterward, Pluto remained essentially a smudge. The best image available before a spacecraft finally arrived there was a handful of blurred pixels from a space telescope, just barely good enough to hint at patches of lighter and darker material on its surface. Scientists could infer, through spectroscopy, that nitrogen, methane and carbon monoxide ices coated its surface. They knew it had an impossibly thin atmosphere. They knew almost nothing else. The prevailing expectation, right up until a spacecraft finally arrived there in 2015, was modest, almost dismissive. Most researchers anticipated a geologically dead world, a cratered, inert ice ball, an interesting fossil from the solar system's formation, but ultimately simple. A place with a story that had already finished being written 4 billion years ago. Within hours of the spacecraft's closest approach, that expectation was not just revised. It was shattered. The first high-resolution images beamed back across billions of kilometers revealed something so unexpected that the mission's own scientists initially doubted their instruments were working correctly. Sprawled across Pluto's equator was an enormous, bright, heart-shaped deposit of ice, later informally named in honor of the world's original discoverer. And the left lobe of that heart turned out to be one of the single most remarkable geological features ever found anywhere in the solar system. A basin roughly 1,000 kilometers across, comparable in area to a mid-sized country, filled to a depth of several kilometers with solid nitrogen ice. Its surface was almost perfectly smooth. Virtually no impact craters marked it anywhere. In planetary science, that single fact carries enormous weight. A cratered surface is an old surface, one that has patiently accumulated impacts for billions of years. A smooth surface, on a world this ancient, means something else entirely. It means the surface has been erased and rebuilt over and over by some genuinely active process. On a world 4.5 billion years old, sitting nearly 40 times farther from the sun than Earth, in a region so cold that nitrogen itself freezes solid, that kind of youthful, self-renewing terrain should not exist. And yet there it was, spread out across an area the size of Texas, glowing faintly under a sun so distant it provided barely enough light to see by. What was actually driving that endless renewal? What could possibly generate enough energy on a small, frozen, sunlight-starved world to keep its surface young for billions of years? is a question that leads directly into some of the strangest geology ever discovered anywhere in the solar system. And that is exactly where we're headed next. Part 5. The world with a heartbeat. The process turned out to be convection, and once scientists understood it, they realized they were looking at something genuinely unprecedented. The nitrogen ice filling that vast heart-shaped basin is not sitting still. It is slowly, patiently churning, like an unbelievably slow pot of soup left simmering on the lowest possible heat for millions of years at a time. Thermal energy leaking upward from Pluto's rocky interior, modest by any earthly standard, but more than sufficient to soften nitrogen ice at temperatures hovering around 35 to 40 degrees above absolute zero, drives a sluggish, continuous overturn within the ice sheet. Warmer nitrogen rises slowly from below, spreads outward across the surface, cools as it reaches the top, and eventually sinks back down again at the margins, completing a cycle that would be utterly invisible to a human eye watching in real time, but that has reshaped the entire basin again and again over its history. From orbit, this circulation leaves behind a visible signature, a pattern of polygonal cells tiling the surface, each one roughly 20 to 40 kilometers wide, their boundaries traced out by darker troughs where the ice is actively descending. The entire surface of that basin appears to refresh itself on a timescale of roughly 500,000 years. In geological terms, that is astonishingly fast. It means any crater that manages to form there from a wandering comet or a stray fragment of debris is eventually swallowed by the churning ice beneath it, pulled downward and erased from the record entirely, as though it had never happened at all. To understand why this matters, you have to set aside everything you know about nitrogen from ordinary experience. At the temperatures found on Pluto's surface, roughly minus 233 degrees Celsius, nitrogen behaves nothing like the invisible gas filling the room around you right now. It becomes a solid, but a strange and geologically soft one. It deforms and flows under its own weight, in some ways similar to how glacial ice flows here on Earth, though at a pace and under conditions so alien that the comparison only barely holds. This softness allows nitrogen to act as an active geological agent out there, filling basins, threading through valleys, transporting material across hundreds of kilometers of frozen terrain. Along the eastern edge of that same basin, the spacecraft photographed something that looked, at first glance, almost unmistakably familiar. Nitrogen ice glaciers, actively flowing down from the surrounding highlands and into the basin below. Dark flow lines streaked down through narrow valleys, spreading out into fan-shaped deposits where the ice reached flatter ground. The exact visual signature glaciologists on Earth would recognize instantly from mountain glaciers here at home. These are not ancient relics, frozen remnants of some long-dead process. They are moving right now, driven by the same volatile cycle that powers the basin's slow convective churn. Climate models built from the spacecraft's data suggest that nitrogen ice sublimates directly into gas on the sun-facing portions of the basin, joins Pluto's impossibly thin atmosphere, drifts across the surface on faint winds, and eventually recondenses onto colder terrain elsewhere. Over the course of a single Pluto day, which lasts roughly 6.5 of our own, something on the order of 1 millimeter of nitrogen ice transfers from one region of the basin to another. It sounds like almost nothing, but integrated across millions of years, that tiny daily transfer adds up to kilometers of material being physically moved around the surface of this world. Glaciers flow downhill under simple gravity, while at the very same time, sublimation and recondensation quietly redistribute ice across the broader landscape, an entire nitrogen cycle operating on a world so cold that water itself behaves like solid stone. The mountains ringing that basin delivered their own separate shock, because at these temperatures, ordinary water ice stops behaving like the fragile, slippery substance you're used to and starts behaving mechanically, almost exactly like rock. It doesn't flow, it doesn't deform easily, it holds its shape the way granite holds its shape here on Earth. The peaks near the basin, rising 1 to 3 kilometers above the surrounding terrain, are built from enormous broken blocks of this rock-hard water ice, evidence of genuine tectonic forces having fractured and shifted the crust at some point in the past. And their summits are white. Not with water frost, the way you might expect, but with methane frost. A bright coating clinging to the highest elevations that creates a visual effect eerily reminiscent of snow-capped peaks on Earth, even though the underlying physics is almost completely inverted. On Earth, temperature falls as you climb higher, so water vapor condenses onto cold mountaintops. On Pluto, methane concentration in the thin atmosphere actually increases with altitude, and at sufficient height the air becomes cold and methane rich enough for frost to condense directly out of the sky and onto the exposed rock below. The result looks achingly familiar. The mechanism behind it belongs to an entirely different world. Further to the east, the terrain grows stranger still. In a region covered by towering blades of methane ice, some standing hundreds of meters tall, arranged in dense, eerily regular parallel rows stretching across hundreds of kilometers of frozen ground. These formations resemble a phenomenon found in only a handful of extremely high-altitude locations on Earth, tall, needle-like spikes of snow and ice, sculpted by sunlight hitting an icy surface at a shallow, grazing angle. On Earth, those formations grow to perhaps a meter or two at most, in rare, isolated conditions. On Pluto, the same basic physical process, given millions of years and an essentially uninterrupted supply of methane ice to work with, has produced a landscape of knife-edged ridges and deep troughs so vast and so geometrically regular that viewed from orbit, it resembles nothing so much as a frozen forest of ice blades stretching to the horizon. This bladed terrain tells scientists something important. Methane ice has been deposited, carved, and reworked across Pluto's surface over enormous stretches of time, confirming that the volatile cycle discovered in the basin is not some isolated local curiosity, but a planet-wide system. One that moves material between hemispheres and between highlands and lowlands as Pluto's long, slow seasons shift across its 248-year orbit around the Sun. And then there were the volcanoes. South of the great heart-shaped basin, the spacecraft's cameras picked out something entirely unlike anything previously catalogued anywhere in the solar system. Enormous mounds with smooth, undulating flanks, some rising several kilometers above the surrounding plain and spanning well over 100 kilometers across. Their broad dome shapes and depressed summits bearing an unmistakable resemblance to volcanic structures. But these are not lava volcanoes in any conventional sense. They are cryovolcanoes, built not from molten rock, but from the slow eruption of icy material welling up from somewhere deep within Pluto's interior. A study published in a major scientific journal in 2022 examined this region in detail and concluded that these features required repeated eruptions from multiple separate sites and an almost unimaginable volume of erupted material, more than 10,000 cubic kilometers, to build the terrain visible today. The near-total absence of impact craters across these mounds suggests the most recent activity there occurred within the last 1 to 2 billion years, and possibly far more recently than that. Elsewhere on the surface, trench-like fractures and what may be an actual volcanic caldera near one of Pluto's larger impact craters revealed spectral fingerprints of water ice mixed with ammonia compounds. A combination that carries real significance, because ammonia is thought to be destroyed relatively quickly once exposed to the harsh radiation environment at Pluto's surface. Finding it there at all strongly implies that whatever eruption exposed it happened recently, geologically speaking, likely within the last billion years. The implication is genuinely difficult to sit with. Pluto retains enough internal heat on a world smaller than our own moon, orbiting nearly 40 times farther from the Sun than Earth does, to drive actual volcanic eruptions. Built not from rock, but from ice. Where exactly that heat is coming from remains an open question. The slow radioactive decay of elements buried in Pluto's rocky core is the most likely primary source, but whether Pluto has also somehow retained leftover heat from its own formation, or perhaps generates some warmth through tidal interactions with its large moon, is still very much unresolved. A 2026 paper examining the full breadth of what has been learned about this small, distant world summarized the situation about as plainly as science ever allows itself to. Pluto exhibits active geology and a genuinely dynamic atmosphere. It is not a frozen wasteland. And its authors suggested something even more provocative, that Pluto should be treated not as some strange exception to the rule, but as a preview, a template for what other large worlds scattered throughout this distant region might also be quietly doing, far from any telescope capable of watching closely enough to notice. Even Pluto's atmosphere, thin as it is, roughly 100,000th the pressure of the air you're breathing right now, supports genuine weather. Layers of haze extend more than 200 kilometers above the surface, built from organic particles produced when ultraviolet sunlight breaks apart methane and nitrogen molecules high in the sky. Those haze particles slowly drift downward over time, settling onto the surface and contributing to the reddish-brown coloring visible across much of the terrain below. Faint winds leave dark streaks across the ice, and the entire atmosphere is, in a very real sense, temporary. Its pressure swells and shrinks dramatically across Pluto's long orbit as the planet's distance from the Sun changes and nitrogen ice either sublimates into the sky or refreezes back onto the ground. Current models suggest the atmosphere is near its peak right now and is likely to collapse sharply within the coming decades, as Pluto's northern hemisphere slides from summer into a centuries-long winter. A world with an atmosphere that periodically collapses, only to slowly rebuild itself again centuries later, is not, by any reasonable definition, a dead world. And Pluto's largest companion, orbiting so close that the two worlds are gravitationally locked face to face in a permanent tidal embrace, turned out to hold its own set of surprises. Surprises that suggested this small, icy moon had, at some point in its distant past, been cracked open from the inside. What the spacecraft found written across that moon's frozen, fractured surface is where we're headed next. Part 6. The moon that froze from the inside out. At roughly 1,200 kilometers across, about half the diameter of Pluto itself, this companion moon is large enough that the two worlds are sometimes described as a double dwarf planet rather than a simple planet and satellite pair. They orbit a shared point of gravity balanced in the empty space between them, locked so tightly that the same face of the moon always points toward Pluto and the same face of Pluto always points back. Before the spacecraft arrived, the expectation among most researchers was straightforward. This moon should be simpler than Pluto. Smaller, colder, with far fewer resources available to power any kind of ongoing geological activity. What the spacecraft actually found instead was a world that had, at some point deep in its past, been torn open from within. The moon's most dramatic feature is an enormous system of canyons and troughs stretching across its equatorial and southern regions, one of them running for well over 1,000 kilometers, a rift valley deeper than the largest canyon on Earth, slicing straight across a world barely a third the diameter of our own moon. Another canyon system in the southern hemisphere appears, based on careful shadow measurements, to reach depths of roughly 9 kilometers, making it one of the deepest canyons relative to the size of its host body found anywhere in the solar system. These are not impact features, scars left by something striking the surface from outside. They are tectonic fractures, cracks formed when the moon's own crust was pulled apart by forces originating from somewhere deep within it. The leading explanation involves ice and the simple, almost mundane physics of what happens when water freezes. If this moon once harboured a subsurface ocean of liquid water beneath its icy crust, an ocean that later froze solid, the resulting expansion, water expands by roughly 9% as it turns to ice, would have generated tremendous stress on the crust sitting above it. That crust would have cracked under the pressure, producing precisely the kind of stretched, fractured terrain visible in the canyon systems today. The canyons, in other words, may be the physical scars of a moon that froze from the inside out, its own internal ocean splitting its face open as it solidified. Whether any liquid water remains hidden beneath the surface today is genuinely unknown. The evidence doesn't require a present-day ocean to explain what we see, only a past one. But the timing remains frustratingly ambiguous. If that freezing process is still ongoing even now, pockets of liquid could theoretically persist at depth, insulated from the killing cold above by kilometers of solid ice acting as a thermal blanket. The moon's northern polar region tells a completely different, and in some ways even stranger, story. It is capped by a dark, reddish patch, visually striking against the pale grey terrain surrounding it. This cap is thought to be built from complex organic molecules, reddish-brown compounds formed from simpler building blocks like methane and nitrogen after prolonged exposure to radiation. The leading explanation is genuinely elegant. Methane gas, slowly escaping Pluto's own thin atmosphere, drifts outward through space, and some fraction of it eventually reaches this moon's frigid polar region, where ultraviolet light from the distant sun and energetic particles carried on the solar wind slowly process it into these heavier, darker organic molecules. Over millions of years, these compounds accumulate, painting the pole with a slow-building veneer of irradiated chemistry. This moon is not manufacturing these compounds on its own. It is catching them, drifting across nearly 20,000 kilometers of empty space, in a slow, one-directional chemical conversation between two tidally locked worlds that will likely never stop happening, not for as long as Pluto continues losing methane to space. If Pluto proved that a large trans-Neptunian world could be geologically alive, an object far smaller and far more distant made an equally important point in the opposite direction. Even the tiniest, most primitive bodies out there could turn out to be scientifically profound. A spacecraft flew past a small ancient world formally designated with a string of letters and numbers, but known informally by a name meaning sky in a language indigenous to the region where the discovery was announced on the first day of 2019, passing within roughly 3,500 kilometers, closer than any previous flyby in the mission's history. This object belongs to that calm, primordial, cold classical population we described earlier, one of the belt's original inhabitants, seemingly formed close to where it still orbits today, and left almost entirely undisturbed for over 4 billion years. It measures about 36 kilometers across, weighs essentially nothing by planetary standards, and its shape turned out to be one of the most quietly informative discoveries in the entire history of solar system exploration. It is what planetary scientists call a contact binary, two separate flattened lobes fused together at a narrow neck, resembling nothing so much as a snowman gently pressed from both sides. The larger lobe holds roughly twice the volume of its smaller partner. Both lobes are remarkably smooth, carrying almost no impact craters at all. A surface that has accumulated barely any hits across more than 4 billion years of exposure to whatever debris happens to drift through this remote corner of space. That emptiness carries real weight for understanding the collision history of the entire belt, something we'll return to shortly. But what matters first is what the smoothness reveals about how this strange little world actually came together in the first place. This is not a body that was violently battered into its current shape through repeated high-speed impacts. It is a body that was built gently and then left almost entirely alone. The shape itself functions as a kind of forensic record. Careful analysis of the alignment between the two lobes, the orientation of the object's spin, the near-total absence of surface scarring, all of it points toward a formation process where the two lobes formed close together within a small, localized cloud of material that slowly collapsed under its own weak gravity. They became a gravitationally bound pair, gently orbiting one another, gradually losing energy through the faint drag of surrounding gas or through slow tidal interactions, until they finally drifted together in an almost impossibly gentle merger at speeds of only a few meters per second, barely faster than a person walking. The collision was so soft that neither lobe suffered any meaningful deformation or damage. A 2026 study using detailed numerical simulations confirmed that contact binaries like this one can form directly through the gravitational collapse of clouds of tiny pebbles in the early solar nebula, a process now referred to as streaming instability. This represents a genuinely different picture from the older model of how small bodies formed, one that imagined countless generations of small objects being gradually built up through repeated high-speed collisions, a violent, grinding process. This little snowman-shaped world suggests instead that at least some of the solar system's earliest building blocks were born gently, quietly assembling themselves out of loose particles clumping together under nothing more than their own faint gravity in a calm and undisturbed environment. Instruments aboard the spacecraft detected clear chemical signatures of methanol on the surface, but found no definitive evidence of ordinary water ice. The surface glows a uniform deep red, consistent with organic compounds that have spent billions of years being slowly processed by cosmic ray bombardment. These are not materials forged under violent, high-energy conditions. They are the patient chemical fingerprints of slow radiation processing in an environment about as cold and quiet as physics allows. This small world is, in the truest sense, a time capsule, a fragment of the original solar nebula preserved in the freezer of the outer solar system for a span of time longer than complex life has existed on Earth. But the revelations pouring out of this distant region have not come only from spacecraft flybys. A powerful infrared space telescope, positioned nearly 1.5 million kilometers from Earth, has recently turned its instruments toward these same distant worlds and uncovered chemistry that no previous observatory was ever sensitive enough to detect. What it found, gas escaping from surfaces that should be too cold to release anything at all, and warm spots on worlds that should have gone geologically silent billions of years ago is exactly where we're headed next. Part 7. What the infrared eye found. A second dwarf planet in the classical belt, orbiting at roughly 45 times Earth's distance and taking approximately 310 years to complete a single lap around the Sun, had long been considered one of the more genuinely puzzling worlds out there. Researchers knew its surface was coated in methane and ethane ices, but the finer details of its composition and whether it had any meaningful atmospheric activity at all remained frustratingly uncertain for decades. Ground-based telescopes simply weren't sensitive enough to say anything conclusive. That changed in 2025 when a research team using the powerful infrared space telescope reported something remarkable: the detection of methane gas surrounding this world, making it only the second trans-Neptunian object after Pluto itself where atmospheric gas has ever been directly confirmed. The detection method itself is worth pausing on. Sunlight, faint as it is out there, gets absorbed and re-emitted by methane molecules floating just above the surface, a process called solar excited fluorescence. Essentially, the molecules glowing faintly in response to sunlight in a way sensitive instruments can pick up from nearly 1.5 million kilometers away. The presence of this gas suggests the world possesses either an extremely thin atmosphere sitting in a delicate equilibrium with the ices on its surface, or something called an exosphere, a region where individual gas molecules simply escape the surface entirely and follow long, arcing ballistic paths before either falling back down or drifting off into space for good. Even more striking was a separate finding from the same telescope, reported by a different research team in 2024. They detected a surprisingly strong excess of mid-infrared light coming from this same world. More heat, essentially, than could be explained by a uniformly cold surface simply radiating away the faint sunlight it absorbed. The excess pointed toward the presence of localized warm spots, small patches on the surface running noticeably hotter than the terrain surrounding them. One interpretation on the table is ongoing cryovolcanic activity, something conceptually similar to the icy geysers already confirmed on one of Saturn's moons, though almost certainly operating through a different underlying mechanism out here in this far colder environment. If that interpretation holds up, it would mean this world, a body roughly 2/3 Pluto's size. Orbiting so far from the Sun that surface temperatures hover around 40 degrees above absolute zero, is actively venting material from somewhere deep inside it, right now, in real time. The finding isn't definitive yet. Those warm spots could have other explanations, perhaps unusual surface textures that simply retain heat differently, or patches of compositional variation across the surface that alter how efficiently different regions radiate their warmth away. But the data is entirely consistent with a world that is still, after 4.5 billion years, geologically alive. Follow-up observations are already underway to settle the question one way or the other. The most massive known dwarf planet, the very object whose discovery back in 2005 forced the reclassification of Pluto in the first place, delivered its own chemical surprise. Despite orbiting at a staggering distance where sunlight itself takes over 13 hours to arrive, this world and its small companion moon have become targets of careful infrared spectroscopy, measuring something called the deuterium to hydrogen ratio locked within the methane ice coating its surface. This ratio functions almost like a chemical signature, a fingerprint that can distinguish between different possible origins for the same simple molecule. Primordial methane, inherited directly from the original solar nebula, carries a different ratio than methane produced through active geological processes deep inside a planetary interior, which in turn differs from methane delivered later by cometary impacts. Measurements published in 2024 by a research team studying both this world and the earlier methane-venting dwarf planet found ratios inconsistent with a purely primordial origin. The results instead suggested that hydrothermal or metamorphic processes occurring somewhere inside these worlds have chemically reprocessed their methane, effectively manufacturing new methane through reactions between liquid water and rock at elevated temperatures, buried deep beneath surfaces that sit at temperatures nearly cold enough to freeze nitrogen solid. This is worth sitting with for a moment, because of what it actually implies. The methane sitting on the surfaces of these distant frozen worlds is not simply ancient frost, leftover chemistry from the birth of the solar system, sitting untouched for billions of years. At least some fraction of it appears to have been manufactured from scratch, inside these dwarf planets, through chemistry that absolutely requires liquid water interacting with rocky minerals at temperatures far, far above anything ever recorded on their surfaces. If this interpretation holds, it means these worlds have, or once had, genuinely warm interiors, warm enough for water to remain liquid at depth, warm enough for rock and water to chemically react with one another, warm enough to drive ongoing geological processes capable of slowly replenishing surface ices from somewhere deep below. On worlds this small, this cold, and this astronomically far from any meaningful source of heat, that is a genuinely remarkable claim. But the chemical evidence supports it, and no cleaner alternative explanation has managed to displace it. The picture only continues to broaden from here. Infrared observations of several other distant worlds, published throughout 2024, revealed volatile ices and organic material on each of them, with compositions strongly suggesting that surface volatiles are being actively replenished over time, rather than simply sitting frozen and unchanged since the moment these worlds first formed. One of these worlds, roughly 1,100 kilometers across, was found to possess a genuine ring system discovered when the object passed directly in front of a distant background star in 2023, momentarily dimming its light in a way that revealed a dense, narrow ring orbiting well outside what's known as the Roche limit, the theoretical distance within which a planet's tidal forces should tear any ring apart entirely. The ring's continued survival at that distance challenges existing models of how planetary rings are supposed to behave and raises a genuinely open question about whether the ring is somehow being actively replenished by material still escaping from the world's own surface. Another distant, rapidly spinning dwarf planet, its elongated shape the lasting scar of an ancient collision that shattered a larger parent body and scattered a family of fragments across its orbit, was found to host a ring system of its own, detected the same way through a stellar occultation observation back in 2017. This world completes a full rotation in under 4 hours, spinning fast enough that it has been physically stretched into a shape resembling a flattened rugby ball. Its surface is dominated by crystalline water ice, which is, on its own, deeply unusual, because prolonged exposure to cosmic radiation should have gradually converted any crystalline ice into a disordered, amorphous form over the course of billions of years. Finding crystalline ice intact suggests either recent resurfacing, some process actively refreshing the surface, or an ongoing input of energy from somewhere, continually recrystallizing the ice faster than radiation can degrade it. What makes all of this even more striking is that the scientific community actually received an early warning about this kind of activity, decades before any of these dedicated missions and telescopes existed. In 1989, a spacecraft flying past Neptune on its way out of the solar system turned its cameras toward Neptune's largest moon, a world that orbits its planet backward, in the opposite direction to Neptune's own rotation, powerful evidence that it did not form alongside Neptune at all, but was instead captured, gravitationally snatched from an independent orbit around the Sun sometime in the ancient past. Most planetary scientists today consider this moon to be a captured member of the very population we've been discussing all night. A trans-Neptunian world that wandered too close to Neptune and got permanently pulled into orbit around it. If that's correct, it is the only large trans-Neptunian body besides Pluto that any spacecraft has ever studied up close. What that spacecraft found all the way back in 1989 was astonishing for its time, and in hindsight prophetic. The moon's surface was geologically young, carrying remarkably few impact craters. Its southern hemisphere was coated in a pale pinkish frost of nitrogen and methane ice, and most remarkably of all, the spacecraft directly observed active geysers, dark plumes of nitrogen gas and entrained dust erupting straight up from the surface to heights of roughly 8 kilometers, before being swept sideways by faint upper atmosphere winds into long, dark horizontal streaks stretching across the ice. These were active eruptions, caught in the act, by a spacecraft simply passing through on its way to somewhere else, on a world where surface temperatures sit at roughly minus 235 degrees Celsius. That single flyby demonstrated, back in 1989, that meaningful geological activity could persist on an icy body far from the Sun, in conditions cold enough to freeze nitrogen into rock-hard solid. In many ways, it should have prepared the scientific community for everything that came later, and in some ways it did. But the sheer breadth and variety of what was eventually found on Pluto, the convection, the glaciers, the cryovolcanoes, the atmospheric cycling, the bladed terrain, still managed to exceed even the expectations that earlier flyby had set. No spacecraft has returned to that moon since 1989. An entire hemisphere, never photographed during that brief pass, remains completely unmapped territory to this day. Its interior structure, the possibility of a hidden subsurface ocean, the actual mechanism driving its geysers, all of it remains unresolved, waiting for a mission that does not currently exist. Every new observation from every new instrument keeps reinforcing the same underlying conclusion. This distant region is not some freezer full of inert leftovers, quietly waiting out the remaining lifespan of the Sun in total silence. It is a gallery of active worlds, worlds with complex interiors and ongoing chemical processes, still operating billions of years after they first formed. And if these small, distant bodies are this restless, this chemically alive, despite conditions that should have shut everything down eons ago, then the environment surrounding them deserves an entirely different kind of scrutiny than the one it's traditionally received. Because something is clearly powering all of this activity from within. And figuring out exactly what that something is, and how these small worlds have managed to stay warm for over 4 billion years in a place this cold and this dark, is exactly where we're headed next. Part 8. The heat that should not exist. There is a moment during every outward journey from the Sun when the rules of physics quietly change. It does not happen at a marked boundary. There is no line in space where warmth becomes cold or light becomes darkness. The change is gradual, governed by one of the simplest and most unforgiving laws in all of physics. The intensity of light falls off with the square of your distance from its source. Double your distance from the Sun, and the light reaching you drops to a quarter. Triple it, and it falls to a ninth. Move 10 times farther out, and it collapses to a mere hundredth. The arithmetic is clean and elegant. The consequences, out where these worlds live, are nothing short of brutal. At Earth's distance from the Sun, solar radiation delivers something on the order of 1,360 watts of energy across every square meter it touches. That is enough to power photosynthesis across an entire planet, to warm oceans, to drive weather systems, to sustain every living thing you have ever known. At Neptune, 30 times farther out, that figure collapses to somewhere around 1.5 watts per square meter, less than 1/100% of what falls on Earth. The warm, energy-rich environment that makes life possible on our world has been stripped away almost entirely by the time you reach the last recognized planet. And Neptune, as we have said all night, is only the threshold. Push further out into the heart of the classical belt, and the numbers become more extreme with every additional step. At roughly Pluto's average distance, solar intensity has fallen to somewhere around 0.08 of a watt per square meter. Sunlight now some 1,600 times weaker than what reaches Earth. If you stood on Pluto's icy surface at local noon and looked directly toward the sun, you would still see it. It would still be, by a wide margin, the single brightest object in the sky, bright enough to cast faint, sharp-edged shadows across the frozen ground. But you would feel nothing, no warmth on your skin whatsoever. The scene would resemble something between deep twilight and a brightly moonlit night here on Earth. You could read a page by that light. You would not be able to warm your hands by it. Push out to the accepted edge of the classical belt, and sunlight weakens further still, thousands of times fainter than what Earth receives. Push out to where our spacecraft currently drifts, and the intensity drops even lower, a single faint point of light delivering barely a trace of energy across an entire planetary surface. Sunlight out there is present. It has simply been reduced by nothing more exotic than distance and geometry to little more than a rumour of its former self. The temperature consequences follow directly and mercilessly from this. Without meaningful solar heating, surface temperatures on these distant worlds are governed almost entirely by a fragile balance between the tiny trickle of sunlight they manage to absorb, the thermal radiation they constantly lose back out into the vacuum of space, and whatever modest internal heat each individual body happens to generate on its own. For most objects out in this region, surface temperatures hover somewhere between 30 and 50 degrees above absolute zero. At those temperatures, nitrogen becomes a solid capable of flowing like glacial ice under pressure. Methane freezes into a hard crystalline material. Carbon monoxide forms a stubborn frost. Water ice takes on the mechanical strength of ordinary bedrock. The chemistry unfolding on these surfaces operates in a regime so cold that substances we think of as gases and liquids in everyday life behave instead like minerals, like stone. These conditions do more than simply make this region inhospitable to life as we understand it. They make it operationally hostile to nearly every tool humanity has ever built for exploring space. Consider, for a moment, the simple problem of power. Every spacecraft needs electricity to run its instruments, to process the data it collects, to keep sensitive components from freezing solid, and to transmit its findings back across the growing gulf to Earth. In the inner solar system, solar panels handle this reliably, converting sunlight into electricity for missions studying Mars, Venus, even Mercury. Even out at Jupiter, 5 times farther from the Sun than Earth, solar power remains marginally viable if the panels are built enormous enough. Beyond Jupiter, solar power effectively dies. The sunlight out there is simply too weak, and any panels large enough to capture a meaningful amount of it would be too heavy and too impractical to launch. Every spacecraft that has ever ventured into this outer darkness has relied instead on something else entirely, a device that converts heat, generated by the slow natural radioactive decay of a carefully chosen isotope of plutonium, directly into electricity. These generators are remarkably reliable and completely indifferent to how far they travel from the Sun. But they are also heavy, expensive to fuel, and limited in how much power they can actually produce. Our current spacecraft out in this region launched with a single one of these generators, producing roughly 240 watts of electrical power at the start of its journey, less than the output of 3 ordinary household light bulbs. By now, years of slow radioactive decay have whittled that output down to somewhere around 190 watts. The spacecraft must run every one of its scientific instruments, keep every sensitive component warm enough to function, and transmit its findings across nearly 10 billion kilometers of space, all on a power budget that would struggle to keep a modern desktop computer running. This single constraint shapes almost everything about how this distant region gets explored. Instruments must be engineered for extreme efficiency. Data must be compressed heavily and transmitted slowly, patiently, over the course of hours. Heaters must be carefully rationed, switched on and off in careful sequence, because running too many systems simultaneously would exceed what the spacecraft can actually generate. Communication itself becomes its own kind of ordeal. Radio signals travel at the speed of light, the fastest anything can move, and yet from this distance, a one-way signal still takes the better part of 9 hours to reach Earth. A full round trip, a command sent out and a confirmation sent back, stretches to nearly 18 hours. Real-time control of the spacecraft is simply impossible. Every single action it takes has to be carefully planned, programmed, and uploaded days or even weeks in advance. If something unexpected happens out there, the spacecraft has to detect the problem and respond entirely on its own, executing pre-programmed contingencies long before anyone back on Earth even knows there was an issue at all. The signal itself grows fainter with distance too, following that same unforgiving inverse square law that governs sunlight. By the time a transmission from this spacecraft reaches Earth, its strength has fallen to something measured in billionths of a billionth of a watt. Capturing something that faint requires the very largest radio dishes ever built, enormous 70-meter antennas, carefully aimed at the spacecraft's exact position for hours at a stretch. And even then, data trickles back at rates so slow that information a home internet connection could download in a fraction of a second can take hours to fully transmit from out there. These overwhelming engineering constraints mean this entire region has never been explored through broad, sweeping surveys. It has only ever been explored through narrow, painstakingly targeted glimpses. We have exactly one spacecraft actively operating out there right now. We have flown cameras past exactly 2 individual worlds in this entire vast population. Everything else we know about the thousands of other objects drifting through this region comes not from up-close photographs, but from telescopes here on or near Earth, squinting patiently across billions of kilometers of empty space at targets that are faint, dark, and painfully slow to reveal themselves. And detecting these worlds from Earth in the first place turns out to be one of the single most difficult observational challenges in all of astronomy, a challenge built from faintness stacked on top of faintness. Motion too slow for the eye or even most instruments to easily catch, and a detection horizon that shrinks dramatically the farther out you try to look. Understanding exactly how difficult it really is, and what that difficulty means for everything we think we currently know about this region, is where we're headed next. Part 9. The search for a needle in a frozen haystack. Finding a trans-Neptunian object from Earth is one of the most punishing observational challenges in the entire field of astronomy, and the difficulty comes from two directions at once, each one compounding the other. The first is faintness, staggering, almost absurd faintness. A typical object out in the classical belt, a few hundred kilometers across, orbiting at roughly 45 times Earth's distance from the Sun, reflecting only a sliver of the already feeble sunlight that manages to reach it, appears from Earth at a visual magnitude somewhere around 23 to 25. For comparison, the faintest star visible to an unaided human eye on the darkest, clearest night imaginable sits at roughly magnitude 6. Each step of 5 magnitudes in this system represents a 100-fold difference in brightness. An object sitting at magnitude 25 is, by that math, something like 40 million times fainter than the dimmest star your own eyes could ever hope to see unassisted. Detecting something that faint requires an enormous telescope, an extraordinarily sensitive digital camera, and exposure times stretching to several minutes per single image. But faintness is only half the problem. The other half is motion, or rather, the near total absence of it. These objects orbit the Sun at distances so vast that their apparent movement across the sky, as seen from Earth, is minuscule. Something orbiting at 45 times Earth's distance typically drifts across the sky at a rate of just 1 to 3 arcseconds per hour, so slowly that within a single photograph it looks completely identical to a background star, utterly indistinguishable from the tens of thousands of genuine stars and distant galaxies crowding the same frame. To find it at all, astronomers must take multiple images of the exact same patch of sky, separated by intervals of several hours, and then painstakingly compare them, hunting for the one single point of light that has shifted position ever so slightly while everything else around it held perfectly still. This technique, sometimes called shift and stack or digital tracking, requires genuinely sophisticated software, programs that test thousands of possible motion rates and directions, digitally shifting each image by a different combination of speed and angle and stacking the results together, checking each time whether a faint, otherwise invisible source suddenly snaps into focus. The computational demands involved are enormous. A single field of view captured by a large survey telescope might contain hundreds of thousands of stars and galaxies. Somewhere among them, there might be 0, 1, or perhaps 2 genuine trans-Neptunian objects slowly drifting through the frame, separating that one faint, genuine signal from the overwhelming noise of cosmic rays, detector artifacts, and every other source of false positive that plagues deep astronomical imaging requires immense processing power and extremely careful, rigorous statistical work. There is a story that captures just how excruciating this entire process can be, and it involves the very same small snowman-shaped world we talked about earlier, the one visited on the first day of 2019. After the spacecraft carrying that mission completed its historic flyby of Pluto in 2015, the mission team needed a second destination, another Kuiper Belt object reachable using whatever fuel the spacecraft had left on board. The problem was that at the time, no known catalogued object lay anywhere within the narrow cone of space the spacecraft could realistically steer toward. There simply wasn't a known target out there waiting. The team had to find one from scratch. They enlisted the help of a large space telescope, dedicating a significant chunk of some of the most competitively allocated observing time available anywhere in astronomy to a targeted search, pointing its cameras at fields of sky lying directly along the spacecraft's projected flight path, hunting specifically for the faint, slow-moving signature of an unknown object sitting at exactly the right distance, on exactly the right trajectory, within exactly the narrow angular reach the spacecraft's remaining fuel would allow it to actually adjust toward. The search consumed dozens of individual observing sessions and sifted patiently through thousands of background sources, comparing frame after frame, testing candidate after candidate. The team eventually turned up several possibilities, but only one of them, the object that would eventually be given its name, lay close enough to the spacecraft's existing flight path and was bright enough for the spacecraft's own long-range camera to reliably observe during its extended approach. The margins involved were razor-thin. If that object had turned out to be a few hundred kilometers farther from the planned flight path, or slightly fainter, or sitting on a slightly different orbit, the entire flyby simply would not have happened. The most detailed observations ever made of a truly primordial Kuiper Belt object depended, in the end, on finding a needle in a haystack stretching across billions of kilometers of the outer solar system. And that needle was found with less than 3 years to spare before the spacecraft would have already flown past the empty space where it needed to be. This is precisely why the known population of trans-Neptunian objects has grown so slowly despite genuinely decades of dedicated surveying. Only a few thousand have ever been formally catalogued and confirmed. Each single one of them represents a real investment, telescope time that is scarce and heavily oversubscribed, enormous computational effort, and careful, patient follow-up observations spread across multiple years, all just to confirm the detection and pin down a reliable orbit. And the objects that have actually been found are, almost by definition, the brightest and nearest members of a population, the visible tip of an iceberg whose true extent remains genuinely unknown. The difficulty only sharpens the farther out you try to look. An object sitting at 80 times Earth's distance, reflecting roughly the same fraction of sunlight as an identical object at 45 times that distance, would appear something like 10 times fainter, simply because it receives so much less sunlight to begin with, and sits so much farther from whatever telescope on Earth is trying to spot it. This double penalty, reduced illumination compounding with increased distance, means the practical detection horizon for these worlds falls off steeply the farther out you go. Current surveys can reliably spot objects a few hundred kilometers across sitting somewhere between 40 and 50 times Earth's distance. Push out to 80 or 90 times that distance, and only the very largest objects, those exceeding 1,000 kilometers across, would be bright enough to register at all. Anything smaller than that at those distances is simply invisible to every instrument currently operating. This observational bias turns out to be absolutely critical for interpreting that sharp apparent edge we discussed earlier, the one sitting near 50 times Earth's distance from the Sun. That decline in known objects might be entirely genuine, reflecting a real physical drop in how much material actually exists out there. Or it might just as easily be an artifact of detection limits, objects that are simply there, sitting quietly in the dark, too faint and too far for any existing survey to have found them yet. Telling these two possibilities apart requires either dramatically deeper surveys, the kind a newly operational observatory is specifically designed to provide, or indirect measurements from instruments that don't depend on catching reflected sunlight at all. And that indirect evidence is precisely what the dust counter aboard our lone spacecraft out there has already been providing, quietly. All along, painting a picture of a region far more populated than reflected light alone has ever been able to reveal. Understanding the collision environment behind that dust and what it reveals about the true age and history of everything drifting out there, along with the staggering logistical challenges standing between us and ever sending another spacecraft to look more closely, is exactly where we're headed next. Part 10. What the silence in the ice reveals. Dust in the outer solar system does not primarily arrive from interstellar space, though a modest trickle of it genuinely does drift in from beyond the sun's influence and contributes some small background signal. The dominant source of dust out in this region is the region itself. Collisions between the icy bodies that populate it, even gentle glancing ones, grind tiny fragments of surface material loose and release them into space as fine debris. On top of that, the steady, relentless bombardment of these surfaces by high-speed interstellar grains acts almost like a slow-motion sandblaster, chipping tiny fragments loose over unimaginable stretches of time and adding them to the local population. Over billions of years, these two processes together have produced a diffuse cloud of dust pervading the entire region, with particle sizes ranging from grains smaller than a speck of pepper up to fragments a millimeter or more across. Once that dust is produced, it does not simply sit still where it formed. It becomes subject to forces the much larger parent bodies can essentially ignore entirely. Solar radiation, faint as it is out there, still exerts a gentle outward pressure on these tiny grains, pushing them slowly away from the sun. The smaller the grain, the stronger this relative effect becomes compared to the sun's feeble gravitational pull at that distance, meaning the smallest particles drift farthest before anything finally brings their motion to a halt. At the same time, a subtle relativistic drag effect, caused by the way sunlight is absorbed and then re-emitted unevenly by a moving grain, slowly spirals larger particles inward over extremely long timescales. The balance between these competing forces, combined with the gravitational tug of Neptune and the other giant planets, ultimately determines where all of this dust ends up and how it distributes itself across the outer solar system. Models of this entire process, carefully calibrated against the dust counter's earliest measurements as the spacecraft first crossed into the inner Kuiper Belt, predicted a fairly straightforward profile. Dust density should peak somewhere near the crowded heart of the classical belt, where the concentration of parent bodies is highest and collisions happen most frequently, and then fall away sharply beyond the belt's accepted outer edge, tracking the same steep decline seen in the population of larger, telescope visible objects. As we already covered, that is not remotely what happened. The dust counter recorded impact rates between 45 and 55 times Earth's distance that exceeded every model's prediction by a factor of 2 to 3, with no meaningful decline anywhere in sight. 3 separate hypotheses have been proposed to explain the gap, and each one, if true, carries genuinely different implications for how we understand the structure of everything out here. The first centers on the physical behavior of the dust grains themselves. These particles are not pure inert rock. Many of them very likely contain volatile ices woven into their structure, frozen water, frozen carbon dioxide, perhaps more exotic compounds entirely. When these icy grains are exposed to solar ultraviolet light, even faint solar ultraviolet light, a slow erosive process strips away that volatile material, shrinking the grain and reducing its overall mass. A smaller, lighter grain responds far more strongly to the outward push of radiation pressure, meaning it can travel considerably farther from the sun before some other force finally halts it or destroys it entirely. If this erosion process is more efficient than existing models had assumed, the entire dust distribution would end up stretched outward, sustaining elevated densities well beyond where the actual parent bodies producing that dust are sitting. This explanation leaves the true source population exactly where astronomers expected it, in the classical belt, but changes how far the resulting dust ultimately travels after being produced. The second hypothesis is closely related and involves a more detailed look at how volatile rich grains behave compared to purely rocky ones. A 2025 study specifically modelled the different transport behaviours of these two grain types and found that volatile rich particles genuinely do respond differently to radiation forces than rocky debris does, with the interplay between slow sublimation, gradual size reduction, and radiation pressure together, producing a noticeably more extended dust distribution than purely rocky models alone would predict. This essentially refines and strengthens the first hypothesis. It can account for a real portion of the observed excess, but on its own, it may not fully explain the sheer magnitude of what the spacecraft measured at the most distant points along its journey. The third hypothesis is the one that carries the heaviest implications. It proposes, quite directly, that the population of parent bodies producing all of this dust actually extends well beyond 50 times Earth's distance, in numbers substantial enough to sustain the elevated dust levels the spacecraft continues to record. If there genuinely are Kuiper Belt objects, even small ones sitting well below the detection threshold of every telescope survey conducted so far, quietly orbiting at 60, 70 or even 80 times Earth's distance, their mutual collisions and their steady bombardment by interstellar dust would naturally produce exactly the kind of local dust environment the spacecraft's detector is picking up as it passes through. This explanation requires no exotic new dust physics whatsoever. It simply requires more material out there, more objects, more collisions, more of a solar system than the accepted maps currently show. None of these three explanations rules out the others. All three effects may well be operating simultaneously, each contributing some fraction to the total excess the spacecraft has recorded. But that third explanation, even if it only accounts for part of the discrepancy, fundamentally reshapes how we understand the architecture of the outer solar system. It implies the belt does not truly end where the visible object counts appear to drop away. It implies that sharp edge near 50 times Earth's distance is, at least in part, an artifact of what our telescopes are currently capable of seeing, rather than a genuine limit of what actually exists out there in the dark. There is further evidence supporting this reading, and it comes from an entirely different angle. The near total absence of impact craters on that small snowman-shaped world the spacecraft flew past on New Year's Day of 2019. Impact craters accumulate steadily over time as a surface is repeatedly struck by smaller impactors drifting through the surrounding environment. The number and size distribution of those craters tells scientists a great deal about how many potential impactors of various sizes exist nearby, and how long the surface being studied has actually been exposed to them. A heavily cratered surface points toward a dense surrounding population and a long exposure time. A lightly cratered surface points toward either a sparse population of nearby impactors, a surface that is simply too young to have accumulated many hits yet, or some active process continually erasing craters as quickly as they form. That small world surface is only lightly cratered, and its age is confidently known, roughly 4.5 billion years, sitting quietly in the cold classical belt since the solar system itself first came together. Crater erasure processes on a body this small, with no atmosphere and no detected geological activity of its own, are essentially negligible. The low crater count therefore points directly and unambiguously at the surrounding impactor population itself. There appear to be far fewer small objects in the cold classical belt than earlier models of collisional grinding had predicted. The small body population out there is genuinely depleted relative to what you'd naturally extrapolate from the asteroid belt closer to home. The cold classical belt has not, over 4.5 billion years, been ground down into a fine powder of endless fragments by constant mutual collisions. It has instead remained remarkably intact, its original size distribution largely preserved exactly as it was billions of years ago. This finding actually sharpens the dust puzzle rather than resolving it. If genuine collisions are happening less frequently in the classical belt than earlier models assumed, then the dust production rate from mutual impacts between Kuiper Belt objects should logically be lower than predicted, not higher. And yet the dust counter continues to measure more dust, not less. Either dust is somehow being produced more efficiently per individual collision than existing models account for, perhaps because icy surfaces simply fragment differently than rocky ones do. Or there are genuinely additional sources of dust sitting beyond the classical belt's accepted boundary, contributing directly to what the spacecraft continues to detect as it drifts onward through the dark. The most economical explanation, the one that requires the fewest new assumptions, remains the presence of unseen parent bodies sitting at greater distances than anyone has confidently mapped. This collision environment also quietly reveals something profound about the deeper history of this entire region. The cold classical belt's gentle, low inclination, nearly circular orbits, combined with its surprisingly sparse population of small fragments, together indicate that this particular region was never subjected to the kind of violent dynamical upheaval that would have shattered its inhabitants and pumped up their orbital speeds. Neptune's ancient outward migration, according to the best current models, mostly disturbed the inner and resonant populations closer to its path, while leaving the cold classical belt comparatively undisturbed, a quiet backwater spared from the chaos unfolding elsewhere. Which means the cold classical belt is, in the truest sense, a genuine sample of conditions in the outer solar nebula roughly 4.5 billion years ago. A region where material accreted gently into small bodies through slow gravitational collapse, where collision speeds stayed low enough to build contact binaries instead of shattering everything on impact, and where the resulting worlds have survived, essentially unchanged, all the way to the present moment. In the inner solar system, that original record has long since been erased, asteroids repeatedly shattered and reassembled, surfaces reworked over and over by volcanism and impact bombardment across billions of years. Out here, in the cold classical belt, those original records still exist, preserved almost perfectly by nothing more than extreme cold, enormous distance, and a gentle dynamical environment that spared this one small pocket of the solar system from the violence that shaped everything closer to the sun. But actually reaching out to study those records more closely is agonizingly difficult, and the obstacles standing in the way are not merely observational anymore. They are logistical, institutional, even material, tied to something as mundane and as limiting as the global supply of a single radioactive isotope. And that sobering set of constraints, the fuel problem, the time problem, the simple fact that no funded mission currently exists to follow up on any of this, is exactly where we're headed next. Part 11. The frontier we cannot yet afford to reach. Even if a brand new mission to this region were formally approved tomorrow, funded in full and given every resource it could reasonably ask for, the sheer practical challenge of actually getting there would test the outer limits of what current spaceflight technology can accomplish. The fuel problem alone is sobering enough to give any mission planner pause. Those radioisotope generators we described earlier, the ones that convert the heat of slow radioactive decay into usable electricity, depend entirely on a single specific isotope of plutonium, and the global supply of that particular isotope is extremely limited. Production in the United States actually stopped entirely in the late 1980s and did not resume, even in small quantities, until a national laboratory restarted manufacturing in 2015, specifically to support future missions like the one currently drifting through this darkness. Even now, in the mid-2020s, that production rate sits at roughly 1.5 kilograms per year. Our current spacecraft alone used something like 11 kilograms of it at launch. A future mission designed to orbit a dwarf planet rather than simply fly past it, carrying more instruments and higher data demands for a much longer mission duration, might require even more than that. The entire supply chain for the one material that makes deep outer solar system exploration possible at all is currently measured in grams per month. Then there is the simple, unforgiving problem of time. Our current spacecraft took 9.5 years just to reach Pluto, travelling at one of the fastest launch velocities any spacecraft has ever achieved. A future mission aiming to actually settle into orbit around a distant dwarf planet, rather than simply racing past it in a matter of hours, would need to carry enough additional fuel to slow itself down and decelerate into orbit after a cruise likely lasting a decade or more. That deceleration fuel adds substantial mass, which in turn demands a larger and more expensive launch vehicle, which drives up cost, which stretches out development timelines even further. Mission concepts built around exactly this idea, orbiting the Pluto system and then pushing onward to study additional Kuiper Belt objects up close, have been seriously studied and proposed more than once. None of them has ever actually been funded. The practical reality, as of right now, is that no space agency on Earth currently has a dedicated Kuiper Belt mission anywhere in its funded pipeline. Our lone spacecraft remains the only one actively operating in this entire region, and no replacement is currently being built to eventually take its place. This means the window for direct, up close, in situ exploration of this region is genuinely finite. That spacecraft's power output will continue its slow, inevitable decline year after year as its radioactive fuel source steadily decays. Its instruments will eventually degrade past the point of useful operation. Its trajectory carries it steadily outward at roughly 14 kilometers every second, and within the coming decades, it will pass beyond the outer reaches of the Kuiper Belt entirely, continuing onward into the true emptiness of interstellar space. When that happens, the only human-made instrument capable of directly measuring the dust, the particles, and the broader environment of this distant region from the inside will simply be gone. Whatever questions remain unanswered by that point will stay unanswered, likely for decades, until another spacecraft eventually makes the same long journey. A journey that would take at least a decade even under the most optimistic scenario, and one that would first require a mission to actually be approved and funded, which, as things currently stand, shows no sign of happening anytime soon. Every single observation of an object in this region, therefore, requires overcoming this same cascading set of challenges all at once. Extremely faint targets, nearly imperceptible motion across the sky, enormous distances that stretch every signal to its breaking point, weak, whisper-thin radio transmissions, severely limited spacecraft power, communication delays measured in hours rather than seconds, a finite dwindling supply of the one fuel that makes any of this possible, and, right now, no funded successor mission waiting in the wings to pick up where the current one eventually leaves off. The entire known population of trans-Neptunian objects, several thousand strong, has been built up over more than 3 decades of painstaking, patient work by survey teams operating some of the largest telescopes on Earth. Exactly 2 of those objects have ever been visited directly by a spacecraft. Every other one remains, for now, nothing more than a faint point of light, its brightness, color, and rough orbital path measured with whatever precision distant telescopes can manage. For the overwhelming majority of them, even the most basic questions remain completely unanswered. What shape are they? What kind of ice actually covers their surface? Do they have moons of their own? Are they smooth contact binaries, or are they irregular fragments left over from ancient collisions? We simply do not know. We cannot know. Not with existing instruments, not from this distance. The physics of this region does more than merely make exploration difficult. It actively, almost stubbornly, resists being known at all. The darkness, the extreme cold, the staggering distances involved, the sheer faintness of everything out there, all of it conspires together to keep this entire region shrouded from view. Every single fact we have managed to extract from it has been won against genuinely formidable odds. And every new measurement, from the dust counter's persistent excess readings, to the deep survey's candidate distant objects, to the infrared telescope's spectroscopic revelations, has consistently shown the same underlying pattern. The reality out there is more complex, more densely populated, and scientifically far more interesting than the models built in the absence of solid data ever assumed it would be. This region operates on timescales that genuinely dwarf ordinary human experience, and at energy levels so faint they begin to approach the fundamental limits of thermodynamics itself. Orbital periods in the classical belt typically range from roughly 250 years up to 500 years or more. An object sitting at 50 times Earth's distance has not completed a single full orbit since long before any of our current nations existed. An object out at 80 times that distance takes more than 7 centuries to circle the Sun even once. A span of time we would call almost unimaginably slow by any everyday human standard. And yet even the processes we would consider comparatively rapid out here, the slow convective churning of that great nitrogen-filled basin every 500,000 years, the gradual flow of glacial ice across a frozen surface at barely a millimetre each week, remain among the fastest phenomena unfolding anywhere in this entire region. Most changes out there play out over millions or even billions of years, entirely invisible to any human observation program that has ever existed or is ever likely to exist. Even the very light we use to study these worlds carries its own kind of temporal distortion. A single photon leaving the surface of an object at 50 times Earth's distance takes nearly 7 hours just to reach Earth. By the time we finally capture an image of that object, the information contained in that light is already 7 hours old, a small delay in most practical terms, but a quiet reminder that every single observation we make out here is really a snapshot of a configuration that has already, however subtly, moved on by the time the data finally arrives. This distant region does not simply present itself for observation the way closer, brighter objects do. It has to be dragged into view, one painfully faint, painstakingly earned exposure at a time. And the engineering and observational challenges standing in the way are not obstacles that any single mission or any single telescope will ever fully resolve. They are structural features of the environment itself. The darkness out there is not some temporary inconvenience waiting to be engineered away. It is the fundamental, unavoidable condition of this entire frontier. Sunlight will never grow strong enough at 50 times Earth's distance to reliably power a solar panel. Radio signals will never travel any faster than the speed of light allows. These distant icy worlds will never become bright enough to be casually surveyed the way asteroids closer to home routinely are. And yet every single time an instrument has managed to operate right at the very edge of its capabilities out there, it has returned data that quietly, consistently contradicted expectations. The dust was supposed to thin out steadily. It did not. The surfaces were supposed to be geologically dead, frozen solid and inert. They were not. The impactor population was supposed to follow roughly the same size distribution found in the asteroid belt closer to home. It did not. The outer boundary of the belt was supposed to be sharp and well defined. The accumulating evidence increasingly suggests it is not. The underlying physics of this region tells a remarkably consistent story. The environment out there is genuinely real, genuinely extreme, and reasonably well understood in its broad outlines. There is no exotic new force at work, no deep mystery about why this region is dark and bitterly cold. That part follows directly from well-established physics applied to well-established distances. The real mystery, the one that keeps drawing researchers back again and again, is what actually populates all of that darkness. And on that particular question, the data keeps quietly, stubbornly outrunning every model built to explain it. Which brings us finally to the strangest and most unresolved thread in this entire story. The handful of distant, wildly stretched out orbits that seem, statistically, to be pointing at something we have never directly seen. Something that, if it's real, would be one of the most consequential discoveries in the history of solar system science. That is exactly where we're headed next. There is a moment during every outbound journey from the Sun when the rules quietly change, and we have spent tonight walking straight through it. Past Neptune, past the last clean line on every diagram, into a region that refuses to sit still long enough to be fully mapped. A boundary drawn with such confidence for 30 years is dissolving under real data. Worlds too small and too cold to move are flowing, cracking, maybe even erupting. And somewhere further out, in orbits so faint and so slow that finding them took years of patient searching, something unseen may be quietly shaping the dark. We do not know yet how this story ends. Nobody does. The spacecraft drifting through it right now will eventually fall silent. And whatever it has not yet found may stay unfound for decades. But that unfinished quality is not a flaw in the story. It is the story. Somewhere out there, past the edge you were taught to believe was final, ancient light is still arriving, ancient ice is still moving, and the map is still being drawn in real time by instruments straining at the very edge of what physics allows. If tonight's journey into the dark helped you drift off a little easier, let it settle. Let your eyes close on that quiet, unfinished frontier. And if you'd like more nights like this one, consider liking this video and subscribing so the next quiet mystery finds its way to you when you need it most. Sleep well.